So it's really a pleasure to present here today. So I will talk about experimental results of rotational energy transfer of carbon monoxide by collisions with argon and molecular hydrogen. So we know So we know that a molecule can vibrate and can rotate in the same time. So in addition to its electronic energy levels, there are also quantified vibrational and rotational levels. Rotational energy transfer can occur, for example, during collisions between two molecules or an atom and a molecule. Let's take this example of collision between a diatomic molecule and an atom. This rotating molecule can pass from an initial rotational state to a final rotational state by transforming the kinetic energy of the atom to rotational energy to the molecule. This is the simple meaning of rotational energy transfer. So why rotational energy transfer is important? Actually, it has great importance in astrophysics since it plays a key role in the phase of collapse of molecular clouds to form stars, in which the process of cooling is very important to continue the collapse and form stars. This process of cooling is ensured by rotational energy transfer. On the other hand, radiative transfer calculations, which are very important to analyze observational spectra and to determine relevant physical and chemical parameters in the interstellar medium, like Octavio described before. These calculations are based mainly on the collisional data giving rotational energy transfer. So there are several techniques to study rotational energy transfer of molecules. So I use here the infrared vacuum ultraviolet Doppler resonance technique, which is a spectroscopic technique combined with the Crazy technique, which is the acronym of reaction kinetics in uniform supersonic flow, which is based mainly on an isentropic expansion between a reservoir in high pressure and a chamber in low pressure, passing the gas through a level nozzle, which allows to generate a uniform supersonic flow, and in which we can reach very low temperatures. So after generating very low temperatures, we measure rotational energy transfer by the technique of infrared vacuum ultraviolet Doppler resonance technique. So it consists to pump the molecule of interest to an initial low vibrational level and study rotational energy transfer after collisions by another frequency. So let's take the case of CO. So for that we use an infrared tunable infrared laser to pump to a non-populated low vibrational level. The molecules of CO will collide with the partner of collision, so it could be hydrogen, argon, or something else, and will relax over final rotational states. So to measure rotational energy transfer, we need to probe every final rotational state here. So for that we use laser-induced fluorescence in vacuum ultraviolet. So we can perform two different kinds of experiments. The first one, which aims to measure the total removal constant, and in which we probe only the initially excited state, and we follow the relaxation from this initially rotational state to the final rotational state. The other one is the spectroscopic experiments, and which aims to measure state-to-state rate coefficients. So for that we need to probe every final rotational state. So we need to enable VUV to do that. So here the experimental setup. So as I said before, we need the quasar to generate a specific temperature, And we need two tunable frequencies, the infrared to pump the populations to an initial vibrational level, and we need VUV to probe. The infrared is generated by an LPO laser, which is pumped by a pulsed Diag laser. So this LPO laser can generate tunable infrared frequencies. The laser will pass through a photoacoustic cell, which allows to record infrared spectra and select the vibrational level to excite. And the laser will pass through the uniform supersonic flow, in which it's pump the molecules of CO and will collide with the partner of collisions, so argon for example. And we measure rotational energy transfer by VUV probe, which is generated by two photon resonance four-way frequency mixing in an xenon gas. To do that, we roughly combine two wavelengths in UV and in visible. These lasers are generated by day lasers, which are pumped by a pulsed Diag laser. So, so after generating the UV here, its cause is the uniform supersonic flow, and it's allowed to probe the final rotational states. And thanks to the by the fluorescence, we can probe every rotational state, and the fluorescence is collected by a photomultiplier tube, which converts linearly the fluorescence to an electric signal. So I start with CO-argon system, which is a good system for understanding intermolecular forces. So here, a typical result of total removal constants in a room temperature for an initial rotational state J equals 6. Here, the time delay between the pump and the probe, and here the intensity. So we can see that at time 0, the total of the population of the partition function is in the initial rotational state J equals 6, and after the population will relax exponentially to a rotational equilibrium at about 1 microsecond. So after the decay factor, or the characteristic time of the decay, will give us direct measurements of total removal constants, and we can as well determine the thermally averaged force section. So we perform also state-to-state rate coefficients measurements. So to do that, we record mainly to two different kinds of spectra. So short time delay spectrum and long time delay spectrum. So for this spectrum, we pump the population to an initial rotational state. Here is J equal 4. Most of the population is in J equal 4, and here are the final rotational states of the transition corresponding to final rotational states, which still not well populated at this time delay. So after typically 1 or 2 microseconds, the rotational equilibrium is reached, and the intensities of peaks here, which corresponds to the final rotational states, will increase, forming Boltzmann distribution. So to measure rotational state-to-state rate coefficients, we divide the population of CO in short time delay by the population of CO in long time delay, taking into account the short time delay and the concentration of the partner of collision. So here are some typical results of state-to-state rate coefficients of CO-argon at 112 Kelvin. For four initial rotational states, J equals 0, 1, 4, and 6. Let's take this example of J equal 4, for example. In black color are the experimental state-to-state rate coefficients given with 2 sigma errors, and the blue color is the theoretical state-to-state rate coefficients which are obtained by closed scoping calculations using new 3-dimensional potential energy surface. These calculations have been done by the group of Stockholm and Bordeaux University. So we can see a good agreement between the experimental state-to-state rate coefficients and the theoretical state-to-state rate coefficients. And we noticed also a good agreement between the experimental total removal constants and the sum of experimental state-to-state rate coefficients. Concerning temperature dependence of cross-section, let's take these examples of J equals 6 and 4. We noticed an increase of cross-section by decreasing the temperature. This trend actually has been seen before in the CO-helium system. So increase of cross-section by decreasing the temperature. But we noticed a cross-section higher than CO-helium. So yeah, it's all for CO-argon, and I give here just some preliminary results of COH2 system. Here the short time delay spectrum for an initial rotational state J equal 1. We see here, so most of the population are in J1. Here 2, 3 are the final rotational states, and here after rotational equilibrium at small time delay, typically 2 microseconds. And here are the total removal measurements, which is laser-induced fluorescence spectrum. And here the state-to-state rate coefficients after data analysis of these spectra. So actually we see a good agreement between the total removal constants and sum of state-to-state rate coefficients. But the comparison with the theory of calculations of François Lick will be done soon when I progress in the experiment. Okay, so in summary, for CO-argon system, we noticed good agreements with theory for a set of temperatures between room temperature to 27 Kelvin. So we noticed also high rate coefficients and cross-section comparing with smaller gases like CO-helium. And we noticed also an increase of cross-section by decreasing the temperature, and this is due mainly to the deepness of van der Waals well. For the COH2 system, experiments and data analysis are in progress, and the comparison with theory will be as soon as I said. So thank you. Before that, sorry, I would like to thank Heidelberg supporting my PhD, Martin Fonny from Sandia Lab, Laura Mertens from Caltech, David Curti from Durham, and Sébastien Le Picard from Rennes University, without forgetting my supervisor, Jens Sims. So thank you.
Thank you. We have time for a few questions for Hamza. Yes?
Could you go back to slide number 3?
Here?
Yeah. Is that a pipe? The brown? Is that a pipe?
Is there? Oh,
Is that a pipe,
A pump.
a pump,
Yeah, of course.
a pipe.
Yeah, just to create very low temperature here in this chamber. Yeah,
It's actually enclosed.
so it's actually tube, so it's tube here. Yeah.
I was wondering why the molecules chose a single direction
Yeah,
from a
yeah, it's a
completely
single
randomized-
direction. It's uniform supersonic flow.
For your CO argon experiments,
Yeah.
If you were to fit that to a shape, would you use exponential energy gap model? I know for hydrogen rotational energy transfer, you get a pretty good exponential energy gap for rotational energy transfer. Do you do the same for CO with argon or CO with?
No.
No. Could you describe that as a Poisson distribution, or is there some simple distribution you would assign to those?
You mean for the spectrum?
Well, for the energy transfer, the shape of the energy transfer.
The shape of energy transfer. Yeah. So actually, I did that. So.
Yeah.
So you mean this shape?
Yeah, shape.
This is due actually. So here the initial rotation space is J4, so it should be here, and here are the rotation energy transfer for J3 from 4 to 3, 4 to 2. So we see that here is easier. The rotation energy transfer is easier here than, for example, for delta J far. So this will make this shape or delta J
So
when
you would
that
try to fit it to a particular form of any sort.
a particular form actually it is no. That's no.
Okay, when you said you have a flow with mainly CO equals 1 and J equals 4, is it 90%, 99%?
Okay, for CO argon, for example, yeah, it's like not more than 0.5% of CO, just to avoid the self-collision of CO and keep the assumption of first order
Yeah, but
process.
how pure is your flow? I mean, you create CO in equal 1,
Yeah,
J equal 4,
Two, yes.
but do you have J equal 3, J equal 5 also, or just J
I have just initially I have just the initial